Okay. Welcome everybody to that course which I called Parallel C++ for Scientific Computing. And as we will see, the title is actually a very short extract of what the course will be doing. So we will talk about parallel computing. And that will include talking about hardware architecture. How does the architecture nowadays support parallel computing? What different types of parallelism does the architecture expose? But we will talk also about parallel programming models. So how can we utilize, how do we have to write code? How do we structure our programs in order to utilize the existing parallelism in the modern machines? C++, why C++? Well, because I like C++, that's one of the reasons. But the actual reason behind it is that C++ is the only language we have available today, which is in wide use, that gives you both. It gives you very low-level access to the hardware, full control over the hardware on one end, so allows you to do very low-level programming, which ensures the performance of your code. And on the other end, it gives you the language support for very high-level abstractions, which is very important, especially when it comes to parallelism, because there we need to reason about things not on the bit level, but we have to build abstractions that allow us to actually orchestrate parallelism on very, very large machines, up to thousands of nodes with millions of cores. And scientific computing, because, well, it's an interesting field. We have a lot of very interesting examples there. Scientific computing is one of those application domains that utilize very large machines, have a lot of potential for parallelism. So I thought to combine these three things in a course, and I'm very happy that you're here to join me today. So let's get going. I'm sorry for that very blurry, but feel free to move over here if that is more convenient to you, because that one is absolutely crystal clear. So what you see here on the slide is a book which I purchased in 1981. So it's one of those books I purchased when I was your age during my undergraduate. And at that time it was just interesting because it was something completely new to think about programming as being a combination of algorithms and data structures. And it amazed me after reading that book and walking through the book that how simple it actually is to do programming. Right? When you start writing code, you usually think, where do I start? And as it turns out, it's very simple to start, very easy, because all you have to do, you have to find a data structure that represents the data you want to work with. And once you have the data structure found out, then all you have to do is to add 3 for loops, and that's it. And these 3 for loops is what we call algorithms. Well, it's a bit more complicated than that, but the essence is exactly that. Programming is finding the right data structures and, on the other end, writing the looping constructs that help us to do what we want to do with the data. The other amazing thing is that this slogan, programming is algorithms plus data structure, is still true today. Absolutely. And I still use that in my daily work and my daily programming work. It describes essentially what a programmer is doing. So that highlights the importance of understanding data structures. And as we will see, to understand data structures in high-performance computing is trivial because it's all about arrays, nothing else. And we will talk about that. And to understand what kind of algorithms we have to use and we can use to utilize parallelism. So finding the right data structure is absolutely trivial, at least for us, because what we want to do, or the best way to use or to orchestrate data in the computer, in the modern computers, is to use arrays. And we will essentially work with arrays all year long. When it comes to what do we want to store in those arrays, there things get a bit more complicated, because there we have to start thinking about what properties do those things have we store. What type properties is it? Is it an integer? Is it a floating point value? Is it something more complicated? And we will kind of touch on type properties a lot, because type properties will help us to simplify and to make our code more versatile in terms of if we know the properties of the types our algorithms work on, and as long as we want to use that very same algorithm on a very similar data type, we can be sure that we can do that as long as the type properties of these two things kind of match. And we will talk about that in detail. And then selecting, developing algorithms requires algorithmic thinking. So that's what we are here. You want to learn how to write code, so we have to learn how to develop algorithms. And parallelization, as we will see, is almost an afterthought. So we will focus very much on algorithms, and then we will see what we can do with those algorithms and how we can parallelize that and speed up the computation as a whole. So this is kind of the overall motto of the course, and we will always come back to that over and over again. So let's start with a bit of administrative things right in the beginning, just to get on the same page, and that's probably why you're here. When I was your age, I was always going to the first lecture and to the last lecture. Was going to the first lecture just to know what to expect, and going to the last lecture so that the professor remembered me. And in between, I only went there when I really thought that things are interesting. So I hope that things will be interesting, but I want to give you at least a rundown of what to expect here. So the course is a first introduction into C++, most and foremost. Anybody here has some experience with C++? Some-ish? I know, you took the course. You, any C++ knowledge? What we will do, I will, if necessary, have a lecture or two about at least the basics of C++, so that you can start working with it and have some idea about the language. The actual experience with C++, you will have to collect yourself during the assignments, and that will help you to follow the lectures and so on. We will talk about C++ standard library, C++ data structures. We will talk about how to, what the algorithms are available to us. We will talk about parallel algorithms. Well, obviously about scientific applications, architectures, parallel programming models, and so on and so on. There's one website, the link is here. It's all you need to know about the course. It's on your Moodle page. The only thing on the Moodle page is that link, so you can go there. That web page has everything related to the course, and I really would like to ask you to follow that, because there I will post assignments, lectures, and things like that. There is a Discord channel. I really urge you to join that, because there we can have discussions, you can ask questions. It's the easiest way to reach me and the TA or other students. And I really encourage you to discuss things there with your colleagues, with your other students here in the class, because that will give you a platform to figure things out. If you have questions, if you are stuck with your assignments and so on. The only thing, please don't share code there. Don't share the assignment results there. But otherwise, feel free to discuss everything. There's a couple of books. I'm listing them here just very briefly, but you will have links to the books on the syllabus, so you can go on the web page and you will see it. I will talk about homework, the project, quizzes, and so on in a minute. Well, we already figured out that the lectures are Tuesdays and Thursdays at this time. There's some grading scheme that I intend to stick to, and in theory, there will be 2 examinations, a midterm examination and the final, but I'm still debating with myself whether instead of doing an actual examination to give you some assignments over a week long or so, and then you can hand in the assignment instead of the examination. All information about the course is there, as I said, so if you follow that, you should be up to date. The lectures, I really, really hope that you will attend them. I was a bad student by not going to the lectures, but I really feel that this course will give you, it's actually the only chance for you to keep up with the material, to go to the lectures. And if you feel that the lectures are boring, or you want to expand on certain things, or you want to know more, please feel free to ask questions at any time, okay? So I'm very flexible. We are only a couple students here, 10 students, so it would be very easy and very flexible to turn that into a discussion. I plan to give you up to 5 individual assignments over the semester. Those focus on writing code. In the beginning will be very simple, just do some simple things. Later on we will do parallelization, we will create some graphs, performance graphs and things like that. So quite interesting things. The first assignment I have already posted. The assignments themselves are hosted on GitHub. Git is a source code repository. I will talk about Git in the beginning of the next lecture in a bit more detail. So you will need to get an account on GitHub for yourself, so you can do that if you don't have one already. It will work that way that you get a link, you click on that link will generate a repository on your GitHub account where you have kind of a starter repository with some starter code. You either download that code to your machine. I have a Docker image prepared for you that you can launch on essentially any hardware. Either install Docker on your machine, download the source code and work there. Or you can also work on Codespaces, on GitHub Codespaces, which is a fully online platform which gives you exactly the same experience. So you don't even have to install anything locally if you don't want to. Whenever you push your results to GitHub, a autograder will be started and will immediately report to you whether the tests that are associated with the assignment pass. So you have a good feedback. And it helps me to simplify grading because I can just look at the autograder results and I know what you have achieved or what's missing. A short word about honesty. I hate talking about these things because plagiarism is something I despise myself, but there's always somebody in the class, well, probably not in this group, but in the larger classes where something always happens. If you have questions about what plagiarism is, go to that link, but you probably have heard about that enough, so you know that you shouldn't copy any code from your neighbor. A word about ChatGPT. In my experience in these programming classes, there's many students who try to solve their assignments using ChatGPT without even thinking about them because they believe what ChatGPT does gives them the answer. From my experience, before ChatGPT, when you were working on a problem for 2 hours and you were debugging a problem for 6 hours, then you were able to solve it. After ChatGPT, we have the situation that you don't spend any time developing your code, but you sit there for 24 hours debugging it afterwards. And the reason is that while ChatGPT gives you a presumably correct answer, it's usually not 100% correct. Sometimes it's completely wrong. Sometimes you get lucky and this is correct. But most of the time you have a very, 95%. So if you use ChatGPT, please expect or anticipate that what it's giving you is wrong. That's the anticipation you should have. And then convince yourself that the answer you got is actually correct. And that will help you, to be able to read code, to understand the problem, and be sure that what you actually submit is a correct answer. My approach to ChatGPT is that I want to train my brain and not theirs. So do yourself a favor, don't use it. If you have to use it, please be aware that if I find that you submit the same code as your neighbor, it's plagiarism. And I don't care whether you got it from ChatGPT, from Google, or whether you verbatim copied the file from your neighbor's computer. I have no way of checking that. If you use ChatGPT, like any other source code you might copy from somewhere else, please cite it and annotate it in your assignment. Tell me, this code I copied from over there. Fine. That means it's not plagiarism anymore. I might deduct some points. I might tell you, hey, okay, you didn't do your homework, you copied everything, but at least it's not plagiarism. Okay, so be honest about it, and that's perfectly fine. In my daily work, I use search on the web all the time, just to understand or remind myself about certain things, because I can't remember everything, and I don't expect you to learn facts. What I really would like you to do is to learn concepts. And then we will go along very nicely. So, without further ado, what do I expect from you, or what would I suggest you do this semester? Well, ask yourself, what do you want to get out of this course? What scientific problem do you want to solve? Do you have a scientific problem you want to solve? Some of you are graduate students. You might have something that is interesting for your PhD or for your master's, where you would like to actually investigate a very particular scientific problem. And I urge you to talk to me about that, so we can kind of integrate that into the course and perhaps help you with your graduate studies. What do you want to learn from this course that can prepare you for your future career, for other courses? Can you write a sequential program to solve your problem? Can you do that today? What is the performance of this code you write today? After the semester, there's another set of questions I would like you to ask. Just ask yourself at the end of the semester, did you actually master the skill set to solve the scientific problem? Can you write a high-performance program solving that problem today? What is the performance of that code? And compare that code you wrote with the performance of the code you can write at the end of the semester, with the performance of the code you wrote today, and see what is actually the benefit. Did things get faster? Was I able to solve my problem in a more performant way? So what we will talk about is a basic CPU model, machine model. So we will talk about architecture a lot, because architecture is absolutely crucial to understand how to gain performance. We will talk about instruction level parallelism as one of the means of parallelism in the code, essentially vectorization. We will talk about multi-core processors. In terms of scientific computing, we will look at how to linearize problems, because as it turns out, all of scientific computing relies on linearization of some complicated partial differential equation or whatever. We will talk about shared memory parallelism and multi-core processors. We will talk about GPUs. And I was able to convince David Koppelman from the electrical engineering department to actually give us a lecture or two about GPUs. He's the absolute authority in that field, and he will happily do that for us and integrate that with overall course. And then we will talk about distributed memory parallelism. We will talk about the big machines, the really big irons, where you have thousands of nodes and millions of cores, and how to deal with that. And we will use real examples to do that. So we will see elements of C++, we will see elements of software organization, we will see elements of software practice, and we will see elements of performance measurement and optimization. So it's not just C++ or not just parallel programming models. It is very much about how to develop software, what are the approaches we can take, and how can we write better code. So as you see, the course is kind of a very, very large set of problems. and I'm not sure yet how we will tackle that. And I really need your feedback so that you can ask me questions and say, hey, I don't get this. Give me more information about this or about that, and I'd be happy to do that as much as needed. So this course is about what algorithms, data, software, and hardware, how does code interact with hardware? This is actually one of the crucial things. With a goal to get best possible performance for the code we write. At the end, you will be able to write software that fully utilizes the hardware. You will be able to describe the architecture mechanisms for high performance. You will recognize opportunities for performance gains, and you can formulate strategies for how to write high performance code for high performance computing machines. Okay, so why do we talk about computing, and what is the significance of scientific computing to begin with? You might have heard of the two pillars of science, and many scientists today either classify as experimentalists or theorists. And over the last 50 years, there has at least been 2 or 3 more pillars being added to the way scientific discovery is being done. Not just theoretical or practical, but computation has definitely found its way into the daily life of physicists, of biologists, and so on, to give them a third pillar of knowledge acquisition. Lately, there is a data-driven knowledge discovery that has been added, and you can think of it as a 4th pillar. And the whole AI thing is probably almost the 5th pillar of knowledge discovery. So we will talk about what do we want to do with that compute power we have, and why do we need it in the first place? Well, there are many things we can't directly verify because we can't go there, or because it's too hot, or because it's too cold, or we can't measure it, or so we need a means to use computation to assess reality. Be it storm surge modeling, right? You want to know where the storm surge will come in when a hurricane hits Louisiana. Will it go here? Will it go there? Will my house be flooded or not, so that I can do evacuation and things like that? That's where scientific computing will be used, or is used. So weather, climate, crash testing, nuclear explosion, simulation, all of that. So computing is generally a good thing. As I said here, it's good for the survival of the planet. If you look at the software landscape of high-performance computing, since high-performance computing has evolved over the last 50 years, essentially in lockstep with the hardware architecture, and high-performance computing was always one of the driving forces of hardware architecture evolution. And many things you have in your laptop today, in terms of architecture and architectural solutions, come from requirements that have been solved 30 years, 40 years ago in high-performance computing. So it's kind of the forefront of all the computing evolution. But since it has evolved over the years, what we see that the different kind of parallelism we have available to us all require different ways to do programming. And this is a pain in the neck. It's just to give you some example. Well, I picked 6 different areas of parallelism, or 6 different technologies, and they have different paradigms. And you see that there are absolutely different ways to program these things. Different C libraries. Partially you have to write assembly code. Partially you have to know special languages to interact with GPUs and things like that. And last but not least, for the distributed computing, you need to, if you look at the widely used technologies today, you have to use something that is called MPI, which is an awful C library, but everybody's using it. So this is what the canon is. So let me kind of give you an overview where all that came from. If we start from a very simple processor, it starts with some memory and a fetch, decode, read, write, execute loop inside the hardware. So the hardware fetches instructions, decodes the instructions, that causes data to be read, then some operation is performed on that data, and then the result is written back to memory. And this is what the processors do all day long, essentially. This is a very simple kind of explanation of what's happening there. So it's a simple model where the CPU fetches the instructions and many cycles per instruction have to work on the data. Later on, in order to improve performance, those cores have gained pipelines. And these pipelines are there just to be able to look not only at the current instruction, but to look at the instructions that follow that, which allows in the hardware to parallelize things. Because if there is a floating point instruction and the core knows that the next instruction is a integer addition or something, then the core can do these two things at the same time. Because floating point and integer units are completely separate in modern cores. So we have these instruction pipelines. The instructions are still fetched, but they are now stored in a stream and kind of optimally even reordered. Modern cores might decide to reorder operations that you wrote your code in a certain order, but the core might decide, hey, I can do this operation that comes five steps ahead of time and do that first, because there's some hardware resources available at this point. But there's still a very long trip to the memory. What's the clock rate of the cores today? Do you know that?
Varies, but we're at like 4.
Well, let's say gigahertz, right?
Let's say 4, 3, I think is
yes.
what I'm running right now.
So about a gigahertz, right? Which means about 1 nanosecond clock rate or half a nanosecond clock rate. So that's 1 billion operations a second, essentially, or 1 billion clock cycles a second. On the other hand, what's the clock rate memory works with? The external memory. Anybody? Megahertz. So you have a disparity of at least a factor of 10 to 100. That means if we don't do anything, the speed of the core is absolutely limited by the speed how quickly data can be moved from and to the external memory. And that's why people introduced caches. Caches are faster memory that is closer to the actual pipelines, that stores the latest data that was accessed during the operation. And if that data happens to be accessed again, then the access times are much quicker, because level 1 cache, the cache that is closest to the cores, operates essentially at the same clock rate as a core. So accessing something from level 1 cache doesn't slow down the execution, the operation of the core. Then there's a level 2 cache, which is a bit further away, a bit larger, and the external memory. So we use special fast memory to keep data and instructions close to the core. And we will talk about that a lot. Further, people have created multi-core CPUs. Around the 2005 or so, clock rates stopped going up to 2005-06. Clock rates were the main reason for cores becoming faster and faster. But then it was impossible to increase the clock rates further beyond 2 or 4 gigahertz. Do you know why? Heat, right. Because the energy that is used is quadratic, proportional on a quadratic law to the clock rate. So with the increasing clock rate, the heat goes up in a quadratic way. So people had to stop increasing the clock rates in order to gain performance. So what the next step was that several cores were put on the same die, and you had more compute power by having 2 cores or 4 cores, or nowadays it's probably up to, I don't know, 128 or 256 cores on the same silicon. But there we have the problem now that after replicating things, the cores have to share memory. The caches need to be kept consistent, coherent, right? If that core and that core work with the same variable, you want for both cores to see the same value. There's no way. So you have to have some additional logic that keeps everything coherent. Even more cores were added later on. So in this case, it's 4 cores. You still have to usually level 3 caches are being added that requires for the cores to share caches. So the logic gets more complicated. What then? Then we ran out of silicon. So the technology didn't allow us to add even more on the same piece of silicon. So people started to have 2 different chips on the same motherboard, which is in the beginning was symmetric multiprocessor SMPs, where all the chips or all the sockets shared the same memory in the same way. These things are called sockets because they are kind of put on the same receptacle on the motherboards. But we still somehow have to keep the caches coherent, even across the chips. And the farther away we get from, or the longer the wire between 2 ends are, the longer it takes, right? Speed of light is still a limiting factor. That means that, well, 1 nanosecond, what distance is 1 nanosecond? Anybody? 1 nanosecond is about a foot. So light travels 1 foot in 1 nanosecond. That means that if your cores are farther away, you limit the amount of data you can transfer in a certain amount of time because, well, it takes some moment to get there. It's not instantaneous. So we have a so-called uniform memory access because it's the same memory all sockets sit on. But very quickly, people realized that this is not possible. So what was created is an asymmetric multiprocessor which sits on top of a non-uniform memory access. And that's what we have today, where each socket essentially has its own associated memory. Each socket can access the memory of the neighboring socket, but that takes a lot longer. So the access time to the own memory is much faster than the access time to the other memory. And that has implications for high performance, right? If I run code prevalently on the socket, I want to make sure that my data is in the associated memory bank. Otherwise, I will pay the price of having to go through the NUMA domain bridge, and that adds performance overheads. Well, the next step was the GPUs. GPU revolution started, I don't know, 20, 30 years ago, started off with video cards. Lately, GPUs are used mostly or very widely for scientific computing for various reasons, and we will talk about those. For now, just acknowledge that there are GPUs. So what are the next steps? The next steps are that you put sockets on a blade. You have not 1 socket, you have not 2, you have 4 sockets on the same motherboard. Then you put the blades in a chassis. So you have not 2 blades, you have many of those. Then you put many chassis in a rack. And then you put many racks in a data center. And then you put the data center on the cloud. And what do you have then? Well, you have then a supercomputer, which is what supercomputers look like. It's just a bunch of racks with thousands of these processors connected with very fast networking. How do we program them? How would you do that? If I ask you, hey, here's a problem. Here you have 1,000 processors, 1,000 nodes, each one comparable to your desktop, essentially compute power. How do you work with those? How do you make sure that these 1,000 nodes actually are useful and are utilized for your scientific computing problem? And this is exactly what we will talk about in the end. So if you go back to that HPC canon, and since you don't see C++ here at all, I thought we have to change that. So what I want to do is I want to use C++ for everything here. So give you a means of using the same language, the same libraries, the same environment for all the problems, which unifies the way you write code. You still have to understand what you're working with, whether you work with a GPU or with a vector unit or with a shared memory, but still the environment is very, very similar, which simplifies things a lot. So what we will do in this semester is to go through these things, and we'll look at each of them separately, and I will give you some examples how you can use C++ for that. Just a comment on the side. I found that quote to be very, well, without any pun intended, funny. It says, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka," which means, hey, I found it, but it's funny. And that is attributed to Isaac Asimov. But it's really true. Because when you start looking at things and you realize, oh, that's funny, that can't be, then you're usually up to something. You're up to a new discovery. Because suddenly something doesn't stick. You know, your experience doesn't conform to the results you're seeing. So let's try to find many of these, that's funny moments during the semester. Okay, so just a short list of where HPC is used today, and that is by no means a complete list. And as you can see, it covers everything from cosmology over weather, earthquake modeling, climate modeling, crash testing, rendering, epidemiology, and so on and so on. So there's essentially no realm in science today where HPC is not being used. How is that done? Well, if you look at a physics problem, you usually see this kind of thing. And you might have seen them, would have kind of said, okay, no, I don't want to do that. Essentially, what this shows you is a system of partial differential equations that describes a particular physics problem. How do we deal with that? How we translate all of this into code so that we can solve these equations? Because most of those equations don't have an analytical solution. At least we don't know any. So we can't just use the formulas and put the numbers in there and get something out of it. That doesn't work. But they describe the behavior of a physical system in space and over time, so that you can predict hurricanes, you can predict car crashes, you know, all these things. And everything is nowadays very nicely described. So how do we do that? As it turns out, there are 3 different types of these systems of differential equations. They are called elliptic, parabolic, and hyperbolic. I'm not going into details here, but things are not as complicated as you might think, because at least we have only 3 classes of systems of partial differential equations. That's one good thing. But if you look in the last row, you will see that all of them can be solved using sparse iterative solvers, right? Elliptic one, the parabolic one. So there's a underpinning way of dealing with all of those. And I'm not going to drag you through the differential equations, so don't be afraid that this will happen. But what I want to show you is how we can formalize, or how can we solve these systems of partial differential equations. If you have that system of these partial differential equations, the first thing you do, you discretize them. And by discretization, I mean, instead of solving the equation on all points of space or time, we find points in space where we are interested in a solution. And these points could be equidistant, they could be in the same distance from each other. And the distance of these points essentially defines the accuracy of our predictions and the amount of computation we have to do, right? And what that discretization gives us, it gives us a system of nonlinear equations. So it's not a partial differential equation anymore, which is good. It's just a system of nonlinear equations. So a bunch of polynomials where we want to solve. So in the simplest case, something like that. We are solving a f of x, where x is something, a vector or something of values we're interested, and we try to find the minimum of that. Not very useful yet, but we can turn system of nonlinear equations into a system of linear equations, because once you have 2 points, there is no reason to actually have the accurate function in between those 2 points, but we can just approximate the function by a linear approximation between those 2 points. And if we do that between all the points, we get a system of linear equations that can help us to solve these things. And system of linear equations is something we know how to solve, luckily. So in the end, after linearization of that problem, all we have to do is to solve a matrix equation where A is some big matrix of coefficients, X is the vector of the values we are interested in, and B is the boundary condition of the whole system we are looking at. And what we want to do, we want to find the values of X that make this equation true. So all scientific computing is this. All scientific computing is linear systems of equations and how to solve them. With AI, this is absolutely extreme, because there these matrices have millions or billions of elements in 2 directions. And that's when you hear about ChatGPT, 3 billion parameters, right? You probably heard about that. Or different large language models, they have a certain amount of, tremendously large amount of parameters. And these parameters is the size of this matrix. Because machine learning and AI nowadays is just an optimization problem where you find the minimum of that function. That's it. But because it's so large, the matrix is so large, it requires a ton of energy. I just heard that Google is trying to reactivate a mothballed power station, nuclear power station, just for their new data center they are building. 5 gigawatt in memory and energy requirements, which tells me that what they're doing is just wrong. It can't be the right solution, right? The human brain takes 20 watts, and they spend 5 gigawatts on a data center just to solve something which doesn't even come close to what the brain can do. So there's something not quite right. Something for you, by the way. I don't think that the big companies will very quickly get away from that energy hungriness they are in, from their energy hunger, because they are so focused on solving the problems. There will be small companies that will solve that problem, and they will come up with solutions to that gives you the same power or even better results than AI can give you today, but with only a fraction of the power requirements. So if you have an idea how to do that, just remember me when you're a CEO of a big company afterwards. I'm happy to take donations and things like that. So just as a business idea, think about it. So all scientific computing is this. Just to give you kind of an idea what scientific computing is all about. So it's all about linearizing the system, the problem, and solving the linear system of equation that is associated with it. So you might want to remember your linear algebra classes in order to kind of really understand what's going on here. So why C++? Well, first of all, you can't learn to program without a programming language, obviously. And C++ is just another good programming language we can use for that. C++ is a language that most directly allows you to talk to the hardware, and on one hand. And on the other hand, it allows you to most accurately express the intent you have in the model you have in your mind. Oh, by the way, C++ is one of the most widely used languages in engineering today. There isn't a field today anywhere where software is involved where C++ isn't part of it. Your car has 100 million lines of C++ code. Well, probably not your car, but the car you will buy once you are a CEO. Those are supercomputers on wheels, because it's a multiprocessor system that is used to make sure that when you hit the brake, the thing actually stops. So our society runs on software, and C++ is one of the fabrics the society is using for that. C++ is very comprehensively and precisely defined by an international standard. And we will use the latest international standard, which is called CSC4700 in this class, which gives you a lot of very nice higher level features that make C++ a language that is very easy to use. And if you know Python, anybody knows Python a bit, worked with Python, you will feel at home. It's almost Pythonic how you can use C++ if you know what you're doing. Last but not least, C++ jobs are one of the most best paid ones in industry. So if you know C++, you're ahead of everybody else. So let's look at a small C++ program, just to get started, to get an impression. Every C++ program has to have one function which is called main. It's where the code starts to run when you launch your program. So main is where things start running. It returns a value, an integer, usually signing or messaging to the environment the code was launched with, the operating system or the shell that was launched, you used to launch a program, whether the execution was successful or not. And the convention is, as long as you return 0, that means that your program ran successfully. It's just a convention. Now, let's create an array of 6 doubles, where the doubles are floating point numbers. It's a special type that allows you to represent, floating point numbers, real numbers. What I'm using here is a data type we will see all the time, which is standard vector. It's the array type of choice we will use because it allows us to manage array data without having to deal with memory allocation. And the good thing is, as you see, we don't see an allocation and we don't see a deallocation anywhere. Everything happens inside that data type. So when I initialize it from these 6 doubles, the appropriate amount of data is memory is allocated, and whenever that data variable goes out of scope, which happens at the closing brace of the surrounding block, the memory will be freed and will be given back to the operating system. So you will never have to deal with memory leaks. I don't know if you have taken C classes or writing C code. There's always a problem that you have to make sure, hey, release the memory I allocated. When I call malloc, I have to call free. C++, you don't have to do that. So it's a very nice way of doing things. So, well, let's try to find the sum of all the values. How do you do that in C++? There's an algorithm predefined in the standard library. And by the way, the std : means this function is predefined for you in the so-called C++ standard library. And reduce, I give the data, the range in between the beginning of my data array to the end of my data array, 6 numbers, and it will by default sum up the values. So it will give us back the sum of the values. Very simple. It's one of those for loops I mentioned, right? This is the data structure. We selected the array data structure, and all we want to do, we want to find the sum of all values. Well, then we call a predefined algorithm that does that, and which is called reduce. And then we print it. And the nice thing about CSC4700 nowadays is that it has a print statement, which is not as awkward as the cout you might have seen. The streaming was a very strange syntax. Essentially what you say, I want to print it here. This is what I want. Then it has placeholders, very much like Python. And then you specify the arguments that have to be moved into those placeholders. And that's it. So it's a very simple way to print things in CSC4700. And we will use that prevalently because of its simplicity. So let's have a look. As I said, C++ or any language has expressions. Those expressions are the things that compute something. They have operands and operators. Well, we haven't seen any operands and operators here because there's no plus, no minus, anything. It's kind of hidden in that reduce, but it's there. The important part of here is that everything in C++ lives in a scope. And a scope in C++ is a pair of braces, opening brace, closing brace. And every variable that is defined inside a scope ends its lifetime at the end of the scope automatically, which allows us to very fine-grained control when variables are defined, when do they go out of scope, when is a memory released, and so on. And we have algorithms, as I showed you, the reduce one or the print line, others. We will talk about types and functions and namespaces in more detail. I'm not going into detail here. I'll skip that as well. So let's ask another question. Why parallel C++? Or why C++ for parallel computing? Because modern computers have more than one core, more than one processor. Or the big supercomputers have more than one computer connected over the network. So many programs require to do what I call many things at once, MTAO. And scientific computing requires a lot of number crunching. You can imagine if you simulate a hurricane, you want to simulate the water height expected in each point at the coastline. So there's a lot of points you want to do computing on. C++ offers us parallel algorithms, which allows to run those reduce algorithms in parallel. We have tasks and data parallelism. We will talk about that. And you have something which is very important in high-performance computing, asynchronous execution. And we will see how that works in C++ as well. Let's have a look at the first parallel C++ program. Well, I took the same thing as before. And the only thing I changed is I pass an additional argument to my reduce, which is called std execution par. And that instructs the system, hey, if you feel like it, parallelize that. Do it somehow in parallel. And for now, we don't care what parallelization means. But as you can see, it's very simple to do parallelization in C++, as long as you use these algorithms that are predefined. And that's why I'm so adamant about using algorithms instead of explicit for loops. We could have used the for loop to do the reduce, right? Just add the number up in a variable and we got the same result. But since we've been using an algorithm, which is in the standard library, all we have to do, we pass an additional argument as a first to reduce, which tells reduce, or the implementation, feel free to run that thing in parallel if you're inclined to do so. Now, in this case, it probably doesn't make any sense to parallelize because 6 elements, the overhead to parallelization would be much higher than just to add these 6 numbers. But if you have 1,000,000 numbers, you will definitely see an effect in terms of speed up. So very important and very necessary addition to C++ standard that is nowadays available very widely in different libraries and different implementations. Yeah, you need a special header file for that, but this is just a detail. We will talk about that in detail a bit more. Okay, so what do we have? Std execution par is essentially a predefined variable that is called an execution policy. And that tells the system that it's okay to execute the loop out of order. It doesn't matter in what order you execute that. And if you add numbers, you don't care whether you add the first 2 numbers and the second 2 pair of numbers and the third one, or if you do it in any arbitrary order, you will always get the same result. So using par in this case is perfectly fine. On the other hand, if you're allowed to execute things out of order, it's obvious that you can run things concurrently, right? Add these 2 numbers on one core, add these 2 numbers on the other core, and then add the overall result. And you will get, again, the same result. So par is a hint to the library, and the implementation is in the end free to decide whether to do it. And it might not do it if you have only 6 elements in there. It might just say, okay, not worth it. I'm doing it sequentially, and that's fine. Now things get a bit more interesting. Because what I want to do here in this course is to introduce you to a library, a additional software package that was developed here at LSU. We called it HPX. And this library has, don't ask me what HPX stands for. Nobody remembers it because that library is being developed for, I don't know, 15 years. And nobody remembers where the name originally came from. But anyway, and the beauty or the good thing of HPX is that it uses the C++ standard and implements it in a better way. And it also gives you additional features on top of the C++ standard, which allows us to control things in much better ways and much easier partially. It gives us also many more features that essentially cover all the spectrum from in that HPC canon, right? And only part of that is available in the standard, C++ standard, but it's all available in HPX. And that's why we will focus on that library. Now you might say, hey, I have to learn yet another thing. No, you don't, because the only difference between HPX and the standard is a namespace. Instead of std, you write HPX. So if you take a standards conforming program, which uses standard everywhere, and you replace it with HPX, you will get a standards conforming program, which does what you expect. One example I want to show you is to use HPX facilities, not to run it on all cores, but to control to run the reduce on 2 cores only. Because it's only 6 elements, so it doesn't make sense to use 128 cores to do the reduce operation. 2 cores are probably fine. So HPX gives you, just as an example, a means to do that by defining a class which is called numCores and attaching that thing with our execution policy. And then the reduce operation will use only 2 cores. So we will come back to HPX over and over again over this course because it will give you the means to achieve all the different types of or to support all the different types of parallelism you have available in your system from a single API, from a single way of doing things. Okay. So HPX execution power is the same execution policy. It tells the library that it's okay to do things out of order. And the numCore thing encapsulates a way to control the number of cores. Just an example. There are many other things what you can control, but this is just one simple example. Okay. Another problem, just as for thought. If I'd ask you, I have an array of numbers, and you tell me how many numbers are unique in that array, how would you do that? How many unique numbers do I have in that list of integers? You could create a set of it out of it. What else could you do? By the way, if you read textbooks, it will definitely do exactly what you suggest. It will use a set, which is a tree implementation that guarantees uniqueness. And by initializing that set from all elements between the begin and end, which is a and a plus 6, because we have 6 elements, it will insert only the unique numbers. And the insertion of every number that is already in the set will fail silently. Nothing will happen. And then we can print the number of elements in our set. Sure, you can do it, but it's slow, very slow. And it's the wrong answer. And you will find over the course that many of the solutions that textbooks give you for algorithms where the textbook was written 10 years ago are simply wrong. And it's another example why using a set, which is not an array, right? It's a tree structure. Using a set is a wrong approach. So let's discuss that a bit more. Solution gives you a correct result, but very slow. The set is implemented using what's called a red-black tree. So it's a binary tree which is self-balancing, which means that whenever you insert a new element in the set, the whole thing has to be reordered. Each operation has complexity, computational complexity. You might remember computational complexity from courses. In this case, the computational complexity in terms of number of comparisons of a set is O n log n. It has to resort the data structure for each insertion. And the crux is that there is a hidden k in front of it, a hidden constant in front of that complexity, which usually is ignored when you talk about complexity because the O notation gives you the correct answer only for infinitely large n. But for normal n's, that coefficient which is in front of it definitely matters. And the k for the sorting causes that k to be very large. So you might say, okay, I don't even need ordering. All I need is equality. Right? I want to find something. I want to figure out if something is in there in my array, in my list of things I'm collecting or not. So in theory, I just need comparison. But what does comparison require in terms of complexity? Comparison means that I have to go through the whole list and compare my value with each of the values. That gives me O(n) complexity. Right? And since I have to do it n times for each number, it's actually squared, O(n) squared complexity, which is very bad complexity. So O(n) gives us just linear search, but comparison, if I have a less than operation defined, it gives us O log n complexity, because you can bisect, right? If you have an ordered sequence, how do you find a value in an ordered sequence? If I give you an ordered sequence of integers and ask you, is this integer part of that sequence? Well, you look in the middle element. If the middle element is larger than the value you're looking for, you go down half, otherwise you go up half. So you can, with O log n complexity, find whether the value you have in your hand is part of the sequence you're looking at. So ordering is definitely what we want to do. So we can't get rid of ordering, because otherwise we could re-implement our set just by looking sequentially in an array and compare each value against it. But that would give us O(n) squared complexity, which is even worse. So what do? We use another algorithm which the standard gives us, which is called unique. And here's the correct solution. We do a sort of our sequence, and then we use the algorithm unique with that sorted sequence. And what unique does, unique reorders the elements in our sequence such that equal elements are next to each other. Okay? And it will give us the first element that is duplicated. So if you look at the sequence, for instance, if I give it the sequence, it will tell me that here is the first unique element. So the distance of that unique element from the beginning gives me the number of elements I'm looking at. Right? In this case, 2. And that's why I'm subtracting A from whatever unique returns. Unique returns the reference to that element, and I subtract the begin, which gives me 2 elements in this case. So this is the optimal solution. While the complexity is still O(n) log n because of the sorting which is required, it has a much smaller k because I'm sorting only once and not on each insertion. So whenever you have an interview and people ask you, hey, how do you find what values are unique in your input sequence? Don't use a set, use this, and they will hire you because they will understand that you understand what you're doing. And the benefit is also that I'm not using a set which is not an array, because this is all array-based, right? All values are next to each other. And we will talk about why arrays are so important and why you should always use arrays for what you're doing. So the bottom line is, what container should you ever use? Well, there's only one answer. Use std vector. Whatever happens in your life, use std vector. So the first question, which container type, which data type to choose, is very simple to answer. Well, somebody might come along and say, hey, why shouldn't I use something else? The answer is not for you. No, absolutely not. We might use other data types in the course, but just for the sake of it. Like that set, right? I just showed you the set, so you know it's there. And if you have some quick hack or something quickly you want to use it, feel free, but not for high-performance computing. So exceptions, not for you. The reason is that the textbooks give you the wrong answers with regard to modern architecture. And the solution or the reason for all of that is caches. Because we have caches in our computers, a set memory that is very close to the cores I mentioned in the beginning. Because we have these caches, and those caches have a very interesting property. Namely, when a value is read by the core, it is stored in the cache, but it not only stores the value itself in the cache, but the 64 bytes that are next to it with it. So memory access always happens in 64-byte chunks. So whatever you read from the external memory, it reads not only the one you need, but it reads the 64 bytes that are next to it. And that means if you have an algorithm that first uses a value and then uses the next value in that array, that next value will be already in the cache, just because the first operation has read it into the caches. And that is where the performance comes from. And that is why I always suggest that you use arrays, because arrays automatically give you that property, that cache. You can use what's called spatial locality in the caches. Spatial locality means that you're using a variable which is located right next to it in memory while you're looping over your data structures. Okay? So if you ask you to use other data structures, well, it's more to make a point. Are we done? Time is not over, right? Still have 10 minutes or so. Couple notes. Well, now we have talked about C++ and why parallel C++. I want to give you a short introduction into what does it mean to work with C++. Because if you are used to Python, you just write your script, you launch Python, and it will run the script and will give you the answer. That is not how C++ works. In C++, you have to compile your code. There's a special program which is called a compiler, which translates the source code, the text you give it, into binary code. And you have to first run the compiler on your code, and only then it produces a binary, and then you can launch the binary to get the result. So it's a bit more complicated, and I want to mention that here. So what compilation in C++ looks like is that you have the source code, which you feed to the C++ compiler, which is GCC in our case probably, or Clang. There are different compilers available, which produces what's called object code. Is binary code, but not executable yet, because it misses references to that print function or to other functions that might be defined in other libraries. Then a linker will be invoked, and the linker is another program which complements the missing pieces with our object code and produces the executable program. So you write your C++ code, the compiler translates what you wrote, the linker links what the compiler produces with library code, with other codes that are necessary, and then the resulting program is being launched. So in Windows, it's probably a .exe file. In Linux or Unix, by default, it's called a.out. So there are different naming conventions. If you need more information about that, there is a lot of information available on the web, and you will get very quickly used to all of that. Now, as you can see, this is difficult, and you don't want to have to invoke many steps when you run things, right? When you want to compile your code, you want to run the compiler, you don't want to run your linker yourself, and so on. So what people have come up with, they have created tools that generate the necessary commands to make all of that happen. And one of those tools is called CMake, and we will use it over the course, which is essentially a family of tools which generates command lines that run the compiler. CMake is a very versatile tool. It can generate command lines for all kinds of compilers, for all kinds of platforms. But the beauty of CMake is that it's 3 lines. You write your own script, which you feed to CMake, and that essentially is sufficient for you to generate all the build system you need. You tell it what the name of the project is, and you tell it that you want to build one executable that has one C++ file. End of story. Then you invoke CMake, and CMake will generate the command lines that are necessary to build that. You store that snippet in a file which is called CMake lists, and you have that CPP file next to it. CMake will do all kind of magic, and in the end you invoke a tool which is called make, and that's all you have to know. And that make will read in what CMake has generated and will build your code. And after that, your demo executable was built and you can run it. So it's an easier way because it allows us to abstract ourselves from the details that are necessary to do the compilation correctly. We will use CMake all the time. So a word about the homework and the projects. Again, we will use Visual Studio Code. I don't know, anybody knows Visual Studio Code? You have seen it? So it's a nice tool that is used for Python programming, but you can do C++ programming in the same way. And Visual Studio Code integrates with CMake very nicely. So it knows how to invoke CMake, so you will not have any problems with that. Assignment 0 will ask you to install everything to get to familiarize yourself with the environment. It's a very simple homework, which if you know what you're doing, you can do in 10 minutes. So it's not complicated, but it's important for you to go through the steps just to familiarize with the environment, familiarize yourself with the environment, because that will help you with the future assignments. You will see the same environment over and over again. Also, as I said in the beginning, we will work with Git and GitHub. Git is a source code control system, and I will talk early next lecture a bit more about Git to give you some introduction. Anybody has worked with Git before? Some of you, but some not. I will give you some introduction so you understand what this is all about. It's essentially a database that stores the versions of your source code files over time. So you can follow all the changes you have made over time. You can go back in time. You can compare things. You can merge two different if two people have edited the same file, you can merge the changes made by two people and things like that. So it's a very convenient tool that allows us to deal with source code management. And GitHub is a web service where this is being hosted, and we will use it for our assignment repositories. In summary, so today single thread of control performance is improving very slowly. As I said, the clock rates are essentially stable. There's no way to improve single-threaded performance massively. There are still some incremental improvements. When Intel comes up with a new processor, these get slightly better in predicting things, or for certain applications they might get a bit faster, but overall single-thread performance is not improving too much. So in order to run your programs significantly faster, what we need to do, we need to utilize the parallel nature of our hardware. And we need to use specialized processing hardware. So you need to know how to reason about and write parallel efficient code, understanding what the hardware is doing underneath. Please note that writing parallel programs can be very challenging because it requires to partition your problem, you have to think about communication patterns. You have to think about synchronization between different threads. So the knowledge of machine and machine architecture and machine characteristics is very important. And we will always go back to that because this is a fundamental of understanding all of this. And we will talk about data movement, because data movement is the most expensive thing we do, especially when we move data from one node in the supercomputer on one end of the data center to the other end, which is, I don't know, 100 feet away or even 100 yards away. And that is very costly. And if you think about speed of light, 100 yards or 100 feet are 100 nanoseconds, right? 100 yards are 300 nanoseconds of speed of light limitation. And that's only in vacuum, not when you have wires. So data movement is one of the most critical things we want to talk about. Okay, so far this lecture. Do you have any questions so far? Please approach me if you have some particular interest in some scientific application. I'm open to integrate that with whatever we are discussing, or if you have some special questions or anything, please approach me. Okay? Thank you so much.